Hello friends, welcome back to my channel Math School. Today we are diving deeper into the number system focusing specifically real numbers. But first, let's revisit the questions I posed in the previous video. 1. Who invented zero? It's Brahmagupta, not Aryabhat. 2. Is 0 a rational number? Yes, 0 can be expressed in the form of p by q where q not equals to 0. For example, 0 by 1, 0 by 2, etc. Question 3. True or false? 1. Every rational number is an integer. It's false because rational numbers include fractions like half which are not integers. 2. Every integer is a rational number. It's true because any integer m can be expressed as m by 1 fitting the definition of rational numbers. Question 4. How many rational numbers exist between 0 and 1? It's infinitely many. Why? Let us explore this with an example of finding 6 rational numbers between 1 and 2. Consider the number line between 1 as x and 2 as y. To find n, here x rational numbers, between these two numbers, divide the interval into n plus 1, that is 6 plus 1, equal parts, since 6 numbers require 7 equal gaps. Now, the length of each part, that is d, is equals to y minus x by n plus 1 equals to 2 minus 1 by 6 plus 1, that is 1 by 7. So if we add this common difference successively to the starting number, we get 1 plus 1 by 7, 1 plus 2 by 7 up to 1 plus 6 by 7, that is 8 by 7, 9 by 7 up to 13 by 7. These are 6 rational numbers between 1 and 2. By repeating this process, dividing intervals into smaller parts, we can find infinitely many rational numbers between any two rational numbers. Question for you, find 7 rational numbers between 5 by 7 and 6 by 7. However, you might notice that there are points on the number line that are not rational numbers. Can you recall perfect and non-perfect square numbers? Okay. For instance, consider the square roots of non-perfect squares like root 2, root 5, root 11, etc. Can we consider root 225? No, because it is 15, which is rational. Now, these square roots can't be expressed as p by q, where p and q are integers and q not equals to 0. Such numbers are called irrational numbers. Additionally, non-repeating non-terminating decimals like 0.10, 100, 1000, so on, or 1.34, 56, 566, 5666, so on, are also irrational. The set of all irrational numbers is denoted by Q complement. Combining rational and irrational numbers gives us the set of real numbers denoted by capital R. Let's represent the irrational number root 2 on the number line. First, draw a straight line to serve as the number line. Take OP as 1 unit and at point P draw a perpendicular line PQ as 1 unit. Connect the points O and Q to form the triangle OPQ. Since it's a right-angled triangle with both legs of 1 unit, by the Pythagoras theorem, the length of the hypotenuse OQ is root 2. With O as the center and radius OQ, draw an arc that intersects the number line at the point A. Point A represents the irrational number root 2 on the number line, that is OA is equals to root 2. But how do we plot root 3, root 5, root 6 and other such numbers on the number line? Have you heard of the spiral of Theodorus? Let's construct it. Start with triangle OPQ as before, where the hypotenuse is root 2. From the point Q, draw a perpendicular line of 1 unit and mark the point as R. Connect the points O and R to form a new triangle. This triangle has legs of lengths √2 and 1, so the hypotenuse OR is equals to √3. Repeat this process from the new point. Draw a perpendicular of 1 unit, connect it back to O, and so on. This creates a spiral where each new triangle adds a right triangle, and the hypotenuse represents root n for successive natural number n. This method allows us to represent square roots of natural numbers geometrically. Here, √1, √4, √9 are 1, 2, and 3 are rational numbers, but √2, √3, √5, √6, √7, √8, √10, etc. represents the irrational number because they are the square root of non-perfect squares. Let's discuss the decimal expansion of real numbers. Why is this important? You will understand as we delve deeper. Find the decimal expansion of the following fractions: 9 by 8, 1 by 11, 3 by 7. 10, 9, 8. After performing the divisions, we get 9 by 8 as 1.125, which is terminating, 1 by 11 as 0.090909, so on, which is non-terminating and recurring or repeating, and 3 by 7 as 0.428571, that is 0.428571 bar, which is also non-terminating, recurring. So we can conclude that every rational number has a decimal expansion that either terminating or recurring, and every irrational number has non-terminating, non-recurring decimal expansion. Now it's your turn to determine if the denominator of a simplified fraction has only 2 or 5 as its prime factors. For example, 4 by 5, 87 by 50, 9 by 16. Will the decimal expansion terminate or not? Comment below. Can we convert a repeating decimal into the form of p by q, where q not equals to 0? Let's take an example where the number is 0.4777, so on. That means x equals to 0.47 bar. How many digits are repeating here? It's just 1. So multiply x by 10. That means 10x equals to 4.7 bar. After subtracting x from 10x, we get 9x equals to 4.3, that is x equals to 4.3 by 9, that is 43 by 90. So x equals to 0.47 bar is equals to 43 by 90. But if x is 3.454545, so on, that means 3.45 bar. How many repeating digits are here? It's 2. So multiply x by 100. That means 2 zeros after 1. And here you will get 100x as 345.45 bar. So x will be 342 by 99. You can calculate it by your own. Now, would you like a quick trick for competitive exams or MCQ? Here's a trick for you. The number of repeating digits in a decimal tells you how many nines will be in the denominator of the fraction. And to get the numerator, subtract the non-repeating part from the full number formed before the repeating sequence starts. For example, 0.5 bar or 0.555, so on, will be equals to 5 by 9. Why? Because the repeating digit is here 5. So just remove the repeating sequence. So number is here 5 and there is no non-repeating part. So 5 minus 0 by the denominator will be how many digits are repeating here? Only 1. So 1 9 will be in the denominator. So it is 5 by 9. But what if the number is 0.64444? So here we get a number 6 which is non-repeating. But 4 is repeating and the number of repeating digit is only 1. In that case, the denominator the number of 9 is okay 1, but the number of non-repeating digits after the decimal point tells you how many zeros will come after those 9s in the denominator. So for the case of 0.64 bar, it will be 64 minus 6 by 90. Why? Because the number of repeating digit is 4. So in the denominator there will be 1 9. And the number of non-repeating digit is 1, that is only 6. So there will be 1 0 in the denominator. And what will be the numerator? It will be the whole number, that is 64. And the non-repeating digit is 6. So write 64 minus 6. That means 58 by 90. Now for more examples, 0.7676 so on, that means 0.76 bar. In this case, the number of non-repeating digit 0, number of repeating digits 2. So in the denominator there will be 2 9s and no 0. And in the numerator the whole number is 76 and there is no repeating part, so minus 0. So the number will be 76 by 99. Next example, 2.5343434 so on, that means 2.534 bar. Here the number of repeating digit is 2, 3 and 4. So in the denominator there will be 2 9. And after the decimal point there is only one non-repeating digit, that is 5. So there will be only 1 0 in the denominator. So in the denominator it will be 990. Now the numerator, the whole number except the repeating part, it is 2534. So 2534 minus the non-repeating part, that is 25. So the number will be 2509 by 990. Using the trick, convert 3.73 bar and 0.91 bar as a fraction p by q, where q not equals to 0. Comment your answer below. Now find 7 irrational numbers between 5 by 7 and 6 by 7. First, express 5 by 7 and 6 by 7 in decimal form. It's your turn to calculate the division part. After calculating the division, you will get 5 by 7 equals to 0.714285. 714285, that means 0.714285 bar, and 6 by 7 equals to 0.857142 bar. Now write any non-terminating, non-repeating decimals between these two values. There are so many, because you know that there are infinitely many numbers. For example, the number must be more than 0.71. That means I can take 0.72. So one irrational number is 0.72, 722, 7222 and so on. I can take any number less than 0.85 and non-terminating, non-repeating. That means 0.80, 81, 82, 83, so on. There is no repetitions. Then 0.725, 255, 2555, and so on, 0.84, 10, 100, 1000, so on, etc. You can write many more. So comment some more examples between 5 by 7 and 6 by 7. Feel free to share your thoughts in the comments below. In our next video, we will discuss the operations on real numbers and the laws of exponents for real numbers. Till then, stay tuned and thanks for watching.